you, Andy. So yesterday, all of you have heard Matei's keynote, and one thing he said is we're going to double down on streaming this year. And this morning, I'm going to be sharing with you some of our plans for the year for real-time and streaming. So why real-time? I think this question is pretty obvious in general, but for some of the audience here, it's typically useful to actually make decisions faster, and sometimes it actually leads directly to bottom line. For example, credit card fraud detection. You probably want to actually flag the fraudulent credit card swipe as soon as it happens, rather than 10 days later where you don't even know where the guy that's actually making the fraudulent transactions are anymore. And there's many other use cases. So in response to this, the industry kind of started this new trend or new generation of systems called streaming engines. And streaming engines typically just takes an input stream, sometimes multiple input streams, and produces an output stream, or maybe multiple output streams. And what is a stream? Stream is really just an infinite list of data that grows over time. About 3 years ago, we kind of saw this trend in Spark, and as a result, actually to try to design Spark from ground up to actually respond to this real-time demand. One example of it is Spark SQL. Spark SQL can actually answer queries interactively very quickly. But the other more important component is Spark Streaming, which was actually introduced 3 years ago in Spark 0.7. This is probably way before most of you have heard of Spark. And according to a survey we did last summer, actually half of the Spark users think Spark Streaming is actually the most important component of Spark. So the popularity is certainly on the rise. Spark Streaming was our first attempt at unifying what we call batch computation, basic computation on static data, and streaming computation. So this is the real-time aspect of it. It has many nice features that were first of its kind in streaming engines, including like built-in state management, exactly one semantics, which I'll explain in a minute. And there's also a lot of features that are very nice for scaling out the computation to very large workloads, such as straggler mitigation, load balancing, and fast-forward recovery. Now, just to touch upon exactly one semantics, what do I mean by that? For some of you that are less familiar with basically streaming computation. Typically, given some operation you want to do in streaming, there's 3 different ways you could do it. One is what we call at least one semantics. So you actually apply that computation at least once for any given event. The second one is at most one semantics. This means you apply the operation at most once. So imagine credit card fraud. Actually, just imagine credit card swipe. Whenever a swipe happens, in the case of at most once semantics, you would basically charge the user at most once. So sometimes you might not charge a user, and sometimes you might charge a user. Doesn't sound very great. What about at least once? It means you charge a user at least once, but you might double charge, you might triple charge. Doesn't sound very nice either. You could actually get an angry email from a user. The first case, you would lose money. The second case, you might get angry emails. Now, both of these cases are actually really easy to do. I can give you a solution that requires no work. For example, for the case of at most once, just never charge your user. Just return immediately in that computation, never run anything. In that case, you have at most once. Even though it's technically, you're always returning 0, but it's doing it at most once. Right? So now, typically what you really want is what we call exactly once, which means if the user swipes a credit card, you charge a user exactly once. So since Spark Streaming was introduced about 3 years ago, we worked with hundreds of streaming deployments with a lot of Spark users and customers. And we've learned a lot in this journey. And one thing we learned is streaming computation typically don't exist in isolation. It's actually typically combined with a lot of other kind of computations. So let's take a look into one use case again, just credit card fraud detection. In the case of credit card fraud detection, typically, you have a stream of data that's just credit card swipes. And then you want to determine for each of the swipe whether you actually have a fraud or not. So these are anomalies that happen. Now just imagine I'm a credit card company, and I've decided I'm going to implement this whole system in streaming. And I'll be using a very simple algorithm. And the algorithm is if the credit card transaction happens outside of the 50 miles radius of my user's residence, I'll flag it as fraud. Now, can I get a show of hands if any of you have gotten a credit card transaction denied because you might be traveling somewhere? Everybody. See, big data still not really solved. Now, this model is obviously not very good, but sometimes you'll be surprised how far is actually, you can actually use this model to get going. But what really happens is, as soon as you get more user complaints, you probably want to look into how you can actually improve the model. Now, how can you improve the model? Actually, you typically involve some data scientist or analyst or modeling team that's actually go and looked at historic data to actually understand the trends and spending patterns better, so you can build better models. And at the same time, you might actually have a different stream that's actually updating some machine learning model that's actually in real time to actually improve the model you're already using in production. And typically, this streaming pipeline might be actually different from a streaming pipeline that's actually happening with the credit card fraud. Because in the case of fraud detection, you want to actually flag the fraud as soon as it happens, maybe in the range of milliseconds or hundreds of milliseconds. Whereas in the case of training a new model, you probably don't want to be actually deploying your model in a 100-millisecond interval, because at some point you might want humans to actually step in and take a look to see whether the model actually makes sense or not. So this use case itself involves multiple streams. It involves actually looking at data, historic data, in an interactive fashion, and also involves running a lot of batch computation. You look at a lot of different use cases. This is not unique. As a matter of fact, a lot of the streaming use cases actually involve many, many non-streaming components. As a result, we actually decided to actually call this class of applications continuous applications, give it a new name. So what is a continuous application? Continuous application is just an end-to-end application that acts on real-time data. It's a very simple definition. With this definition, you could almost call any application a continuous application. So since we studied this pattern, we wanted to look at how Spark can actually simplify the building of continuous applications. Now, what makes building continuous applications difficult? And I think there are two reasons they are difficult to build. The first is it's very difficult to actually, in general, integrate streaming systems with non-streaming systems, which is actually typically necessary in continuous applications. It's difficult to actually have interactive analysis on live streaming data. It's very hard to run batch computation on historic streaming data with a consistent view of the data. It is very hard to actually output streaming data onto some relational database in a consistent fashion with exactly one semantics. And it's also very hard to do machine learning on streaming data. And the second one is streaming computation model is extremely difficult. It's difficult to understand, it's difficult to learn, it's difficult to reason about. Let me give you one simple case. It can't really get simpler. We have a stream with some traffic logs. We pipe this stream into a streaming engine, and all we want to do is to aggregate some count. So I want to see how often each page gets visited at any given moment. And maybe I'm doing just some simple analysis after this. Maybe I'm actually charging my clients based on how much traffic I have generated for their website. Now, this seems really simple in this case. What can go wrong? It turned out there's a lot of things that can actually go wrong. For example, one of the processes that's actually collecting the logs might be slow and send you the records or the logs that are actually delayed. Some logs might actually literally show up 2 days later. In a distributed system, you might actually have some nodes that are outputting your data to your MySQL database, and the other nodes are actually not functioning and not outputting, so you're actually getting partial data. Your whole pipeline might fail, and when it recovers, it might actually give you an inconsistent result. There's a lot of other problems that could happen. And which actually leads to streaming computation model being extremely difficult in 3 different dimensions. The first dimension is data. It's very hard to reason about data in streaming computation because data might arrive late, and data have varying distributions over time, which means one algorithm that might work in a particular given instance of time might not work in the future. Processing is fairly difficult because over time, your logic might actually change. You want to apply new machine learning algorithm. You might want to actually change your whole algorithm completely. And there's also new kinds of operations, such as windowing and sessions. And last but not least, the output is actually difficult to define, because now you have some sort of time span. You need to define what output actually means over time, and how do you define correctness. So for the past few years, we've been thinking about how we can actually simplify streaming computation, because we don't want only the PhDs in computer science that can actually understand this and build robust streaming applications. We want to really take it to the scale to the masses. And I think finally, we have a satisfying answer that we ourselves are happy with. And I'm going to share with you today. And what we're calling this structured streaming. And it comes with one simple realization, which is the simplest way to perform streaming computation is to not having to reason about streaming. And you heard me right. I did drink my coffee this morning. I'm not making this up. The simplest way to perform streaming analytics is to not having to reason about streaming. What do I mean by that? So in Spark 1.3, which was early about a year ago, we introduced data frames. And what data frames exposes is a very simple API that's similar to the tools that people have been using on their single node tools. And you can use data frames to interactive and in the batch mode, deal with historic data. So we thought, what if in Spark 2.0, we just expand data frames and generalize it to deal with infinite amount of data, and introduce a new concept, a new API called streaming data frames. So you can run the same data frame operations just on a stream. So a new API in Spark 2.0 called streaming data frames. But then we thought nobody really wants that. It'd be so much easier if you have a single API with just existing data frames. So that's what we actually did, structured streaming. It's essentially extending the pre-existing data frame API as a high-level streaming API that builds on the Spark SQL engine. And what it does, you could actually run the same data frame operations over a stream with new operations such as event time support, windowing and seshing, and streaming specific sources and sinks. And this is our attempt, second attempt, and I think maybe the best so far, to actually unify streaming, interactive, and batch queries so you can substantially simplify continuous applications. Examples such as aggregating data in a stream and actually output it into some MySQL database should just work out of the box. Or even better, maybe just within Spark, you could actually query directly the state that's being accumulated, aggregated. And you should be able to pipe it directly into the machine learning library in Spark and use that on a live stream. So for the next 5 minutes, geek warning, I'll dive a little bit more into the details, which is probably atypical for a keynote. But bear with me for those that are slightly higher level. And I think for those developers, you probably actually like this. All right. So let me explain the model. First, we have time. This is just your normal time. There's nothing special here. And we have a concept called a trigger. And what a trigger is, it just defines how often you should run some data frame operation. All right. In this case, I have a trigger of every second. So every second, something's supposed to happen. Now, from the beginning of time to the first second, my stream has accumulated some data. In this case, I've defined a data frame query. Let's say it's just some simple aggregation. So it's the simplest one, just count. I want to count how many records I have. Now, this will output basically one record when I run this query on the data that's accumulated from time 0 to time 1. And I just want to output all of this, which is a single number out, to some output. Now, in time 2, I've accumulated more data. So at time 2, I have all the data from time 1 plus the data from time 1 to time 2. And I have my same query again, just count. Now run this count on all the data, and then just give me another number. And I output this number again. And same thing with time 3, except this time I'm running all the data from time 0 to time 3. Right. Sometimes, in this case, we'd actually output all the data all the time for my computation. Sometimes you might actually want to output delta. So this is, for example, if I only run, if I'm basically just doing some ETL and have new data that arrive, maybe I only want to just output only the new data, not all of the data. Right, so just to recap this very simple model, there's 4 concepts. There's input streams or input sources. It's really just a table that's append only. So it keeps growing over time. It becomes infinite. And there's queries, which are just typical normal data frame or SQL queries with new operators for windowing and sessioning. And there are triggers, which indicates how often this query gets run. And there's output modes. And I think we're going to support 3 different output modes. It includes complete, which is always output all the data. And then delta, which is to output, obviously, only the differences between the different triggers. And then update in place, so we can actually update some external system in place directly. All right. Now, let me give you a couple more examples, just slightly more concrete to help you understand this. Let's say in the case of if you're building a streaming ETL, which is actually, turns out, one of the most frequent use cases for doing streaming is to ETL something continuously. So I have data that's in S3 on some bucket, and then I have some data, say, like log files in JSON. I just want to transform it to Parquet files so it's more efficient for querying. So the query here is very simple, just some simple map that turns JSON into Parquet. And for the purpose of this application, I just want to run every 5 seconds. And output modes is I want to basic deltas only for new records, and I'll output it directly back into some S3 buckets. This is how I would define this job. Now, the second one, which is similar to an early example, is to run page view count. I just want to count how many times for each minute each of the page on my website has been visited. So the input might be some logs that's generated by my HTTP server in Kafka. It's coming from Kafka. And then the query is very simple. I'm using sort of a SQL query to actually explain it. It's basically just counting, grouping by the page and the minute. And trigger is, again, I want this slightly faster, so I want to run it every 5 seconds. And the output mode is I just want to update directly in my SQL database I have. So I don't need to query in Spark or anything. I can just query the MySQL database I have. Now, the nice part about actually this one is sometimes data might arrive late, which I was talking about in my early example. And conceptually, this should actually automatically correct my output if I update in place when the data is arriving late. So if some data arrives like 2 days later, my MySQL database that contains actually all the accounts will get automatically updated. So some of you are suspicious, I can see from your face. First, I walked up stage and told you the best way, the easiest way to do streaming is to not think about streaming. And now I'm telling you, we should just run all the data all the time. If I want something to happen at time 3, I run this query on all the data from time 0 to time 3. What's this guy smoking? All right. So what I've just explained to you is actually logically how you should reason about this new model, structured streaming. Essentially, you're just applying data frame operations on static data and think about data from 0 to like some time when the query is run. But when we actually execute it, this is actually very similar to how data frames always been executed. What this logical programming model is giving you is making it as simple to specify streaming queries as just static data. And then what it really generates is for all the operations you're doing, we generate a logical plan. And Spark, actually through the Catalyst optimizer, is going to turn this plan into a continuous and incremental query that will actually run in an efficient mode, rather than running through all the data all the time. Let's go back to some aggregation example. Let me actually show you some code of what this would look like. So this is like how you run some aggregation in data frames. It looks fairly. For those of you less familiar with data frames, it's probably self-evident what's actually going on. We're just reading some JSON data from S3 logs. And then I'm grouping by a field user ID. I'm just aggregating, and we count, for example, or sum up the total amount of time my users have spent on each of the page or each of the user. And I want to write it out to a JDBC database. This is how we express this against static data. So under this new model, the way you actually express this for streaming continuous aggregation is to just replace those 2 calls with .stream. And now you can actually drop new files, new logs that are shipped from maybe some other system into that stream. And every time a new file appears, it would actually pick it up and run through this pipeline, and then actually output it in place, in this case, to some MySQL database. And of course, it would be bad if you run this query a year from now on all the data from now to the year later. So the way it actually works is the first time Spark SQL sys actually a JSON file in the S3 bucket, it's going to do some aggregate. The second time, a new block of data arrives. Spark SQL is going to do the aggregate, except in the incremental fashion. So we only be aggregating on the latest data, and we actually combine automatically the data from historic aggregates without actually users having to worry about this at all. And when the new one arrives again, same thing will happen over and over and over again. So this is actually not something we're only doing about streaming. As I said, continuous applications really needs more than just streaming. And as a result, the rest of Spark will actually follow and be revamped to support this. So for example, one thing that should actually work out of the box, interactive query against streaming data should just work because we're using the same data frame abstraction. There's only a single API. And the second is Spark. We've introduced a new Spark data source API that can actually support exactly one semantics end-to-end. And the reason this is worth highlighting is actually a lot of streaming systems, I think Spark Streaming might have been one of the first streaming systems that support exactly one semantics. So you don't want to charge a user either less or more times. It turns out a lot of the streaming engines work with exactly one semantics within the engine itself. But as soon as you actually want to involve some output operations, it's actually very difficult to guarantee you have exactly one semantics. So within the engine, when I'm doing all my aggregates and all of that, I can guarantee records gets processed once. But as soon as I want to actually write it out to say MySQL, Oracle, any other things, exactly one semantics breaks. Here, we actually want to have exactly one semantics end-to-end, which means from beginning to end for all of this. And we have different output mode supports that supports actually writing out all the data, just partial data in the Delta fashion, or updating data in place. Right? And machine learning algorithm will also be updated to actually support all of this. So besides a very simple programming model that you only need to really think about batch data because you all have already know how to do it just by using the rest of Spark or from other systems, what are other things that this can do that's actually difficult with other engines at the moment? I think there's a few things. One is worth highlighting. It's actually very difficult to do ad hoc interactive querying directly on the stream in a consistent snapshot fashion. And the second is dynamic changing queries. I touched upon this earlier when I was talking about credit card fraud detections. Maybe sometimes you want to change your algorithm completely, and you don't want to bring down your entire streaming applications or continuous applications. So this should actually support removing and adding new queries automatically, dynamically. And of course, you also get the benefit of Spark, that you can have elastic scaling, you can have fault tolerance, and all of that in this new engine. So we keep all the nice perks Spark always had, and we're adding many new features with this much simpler programming model. And really, what we want is if you need to build ever something like this, or even more complicated this, it should be a lot simpler. A lot of things should just work out of the box without you having to worry about all the nitty-gritty details about streaming. So I'm just going to end the talk with a little bit of timeline. As Matei announced, Spark 2.0 will probably be released at the end of April or in the beginning of May. In Spark 2.0, we'll be having this API foundations built up. And really, it's not a lot of new things from users' point of view because it's really just data frames. There's no new thing to learn. It's just a new data frame API and plus the .stream functions. And then there will be, in the first version, Kafka data sources with the file system data sources, file system data sinks, and also databases, because we thought a lot of you probably have some relational database running, and we want actually to integrate out of the box with that, with basically the correct semantics. So you don't have to worry about doing that. And it will have to also support for event time integrations. In Spark 2.1 and beyond, it's a little bit hard to predict where exactly each version the features will land, because we're going to put a lot of efforts into actually making this expressible in SQL, so actually even some of your analyst friends can actually use this without typing any code. And then there's BI app integration that's built in, plus other machine learning sources and things, and streaming sources and things and machine learning. All right. So this is the end of my talk. Thank you. Michael Ambros will be giving a talk, I believe it's one of the first technical session of the day, to talk about how this actually connects with the rest of Spark structure. I think the title of the talk is called Structuring Spark from Streaming all the way to Data Sets to Data Frames. If you want to know more about the details of this, I encourage you to check out that talk. Thanks a lot for coming.